Hi, in this video we are going to look at further application using TDS relationship. So in this series we start with the two TDS relationship. In the first application in the last video we look at finding the entropy change delta S in liquid and solid. It's for those two, and it has own equation. And now we're going to look into another substance, ideal gas. What happens how do we solve delta S, the entropy change for ideal gas? That's our goal for this video. So start with ideal gas. We can use our ideal gas equation. That's going to be PV equal to RT, right? And this is our small v, RT. And now let's take a look. Our first TDS relationship, we have ds is equal to du over t plus pdv over t, right? Okay. Now let's take a look. What's our u? For ideal gas, we also know our since CV, specific heat for constant volume, is equal to du over dt, and our Cp is equal to specific heat at constant volume is equal to dH over dt. So knowing that, we're going to substitute right here. du is going to be equal to Cv dt. Then that's over t, and then plus our pdv, our p over t, we can write over here. P over t is going to be equal to r over v. So r over v dv. Okay, so those are going to be our two simplified version for ds. Then we want to try to find delta S, so we need to integrate. So delta S is equal to S2 minus S1. That's going to be equal to integration of state 1 to 2 Cv over T dt. Then plus, when we integrate this term, we know R is ideal gas constant, so that's taken out of the integral will be R, and integration of 1 over V, that's gives our natural log V2 over V1. Okay, and be aware this is CV here. We know CV is actually a function of a temperature, right? So here I'm actually going to write down CVT dt. That just remind me that specific heat is a function of a temperature. We learned before, when temperature increases, it's going to be harder to more energy required to raise up 1 degree Celsius. So that CVT value increases as well. Okay. So this is actually a very good equation. We're actually going to use it later on. Let's just put on hold. This is very helpful. So far, this is the equation we have for ideal gas for entropy change. Now let's look at another second TDS relationship. This is the first one. Our second one, we have this ds is equal to dH over T minus VdP over T. If you needed to remind yourself on those two equations, you can go back to the previous video about TDS relationship. Okay, so knowing that, we can go ahead substitute our dH right here, which is our Cp dt into this formula, and over T minus. Okay, so what will be V over T here? We can go ahead trying to derive from this ideal gas equation in another form, V over T will be equal to R over P. So using that, this V over T is replaced with R over P dP. That's our ds. What we can do is we'll integrate. When we integrate this, we get delta S equal to S2 minus S1. And then we'll have integration of 1 to 2. Cp, again, I want to focus. The Cp is a function of a temperature as well. So will be Cp T dt over T. Now let's go ahead integrate the second term. We know 1 over P integration will be natural log of P2 over P1. Now we have our second entropy change for ideal gas equation, for our ideal gas, right? So those are the two. I mean, those two equations still seems to be, cumbersome, right? They are not really sleek, they're still pretty difficult to put our hands around to realize how do we use it. So now I'm going to continue to look into this. What we're going to do is looking at two different methods. The first method is going to be approximate analysis. So we're going to look at if we're going to estimate. So for this one, we're going to assume this Cp and the Cv, the specific heat, they're going to be a constant. Even though we said it's going to be function of a temperature right here, but we'll assume it's going to be a constant. So if that's the case, what's going to be our first equation become? This delta S, this entropy change for ideal gas, will become this Cv. It's going to be a constant that can be taken out from the integral. What we will have is going to be Cv. We're going to use average temperature value. Then what's going to be integration? Once this taken out of integral, we'll have 1 over T. That'll be natural log T again. So it will be T2 minus T1. Then the rest, we'll just copy down R natural log V2 over V1. Okay. And a quick review, where do we find this Cv value for ideal gas? That's going to be from our table A2B, right? A2A is at 300 Kelvin, the room temperature. A2B is at different temperature. Okay. Now continue using method 1. How about this equation? What will we get? We'll have delta S. Since Cp here is going to be considered as constant, just as how we assume Cv is a constant. So Cp is taken out of equation and we are using the average temperature. And integration, that'd be T2 over T1 minus R natural log P2 over P1. Now we have another formula to solve entropy change for ideal gas, and our assumption we use for this one here, if they are specific heat is constant. Here you might wonder, there are two equations here. Which one do we use? It's up to you. Whatever is easiest. They both gonna get you the same answer. Okay, but there's always one that's gonna be easier. So that's method number 1. Now let's think about method number 2. Method number 2 is exactly the opposite. We're going to assume this Cp and Cv, they are indeed function of a temperature. So we cannot really take them out of the integral anymore. But because of this, we actually introduce another parameter. It's actually in our ideal gas table, which is table A17 and above. In there is a parameter called S0 T. It's going to be time to use this now. S0 T is going to be defined as this. Okay, so this T prime here, it's an arbitrary reference temperature, right? And S0 is a function of temperature only. Okay, so because of this, we can go back to actually this formula only. Because, let's take a look. From here, we're going to see this is Cp dt. This entire one, we're going to see that's going to be equal to, I'm going to write it down. What's that equal to? That's equal to our T2 and T prime Cp dt over T minus T1 Cp T dt. Okay, so this is what we highlighted in that equation. Now we have another form for that. So going back to this equation, what do we have another form of delta S? Delta S is going to be, and here, this is going to be equal to S naught T2. And this here will be S naught T1. Knowing that, this equation right here have totally changed its form now. It's going to be S naught T2 minus S naught T1, then minus R, copy that down, natural log P2 over P1. Again, where do we find this value? S naught T2, and which is only a function of a temperature. That's from our table A17 and above or beyond. Okay. Well, that's the end of this video. So, quick recap. We have done a lot of derivation. Okay. Our goal here is to find formula for calculating ideal gas for entropy change for ideal gas. And we start with TDS relationship. And when we derive it, we have those two formula. But we're not satisfied with that. We continue to derive. We made two different methods. The first method is assume Cp and Cv, the specific heat is constant. Here, we come up those two equations. So if there's something needs to be major paying attention to, it's going to be right here, right? Those two. That's going to be our method number one. And when we use method number two, you realize we only have one equation here. That would be the only one equation. For this method number two, we assume the specific heat does change with the temperature, and we're going to use table A17 above to help us to solve it using this specific formula. Okay, so that's the end of this video, and I can't wait to show you the application of it in the next example. All right, I'll see you then.